Alright, so we're going to do problem from chapter 6. The first problem we want to do is problem 9. A 3.5 kilogram block is pushed along the horizontal floor by force of magnitude that's 15 Newton and angle that's 40 degrees with the horizontal. So let's draw the diagram first. So you have the floor and you have the block and the force is applied. The diagram is drawn like that, so you can and this is your F, which is 15 Newton, and the angle here is 40 degrees, and the mass of the block is 3.5 kilogram. The coefficient of kinetic friction between the block and the floor is 0.25, so our mu k is 0.25. And so you also calculate the magnitude of the frictional force on the block from the floor and the block's acceleration. So what is the frictional force? So in this case, because the block is moving, so you'll also find the kinetic friction, and you'll want to find the acceleration of this block. So the first thing we do is that we need to draw a free body diagram based on the information we're given. So let's say take this dot as the center of the mass. So you have gravity, so that's your mg. You also have normal force, and you also have this external force, which is 15 Newton applied at this in this direction. Also, because it's moving, the whole thing should move rightward. Then then there's a kinetic friction that's acting to to slow it down. So the frictional force is on the floor. So this is your Fk. So we can, because it's a vector, so we can place the vectors right here. So this is your Fk. So based on this diagram, you can see that altogether there are 4 forces acting on the block. You have normal force, the gravitational force, the frictional force, and also the external force. So in that case, how do we find the frictional force? The equation for the frictional force is this. So you have your Fk, if you remember, that's your mu k, which is given 0.25, and then times the normal force. So the question is, what is the normal force? If we look at this diagram, you can see that this force has a magnitude of 15 Newton. So we can resolve this vector into x and y component. So that's if we resolve it into x and y component and express that in unit vector notation, you will have 15 and then cosine 40 degrees, and because this is the force, you have a positive, so this is your Fx, and then you have your Fy. And you can see that your Fx is positive and your Fy is negative. So you should have 15 cosine 40 degrees I hat, and then the y component is you have to manually put a negative sign in front of it. So you have 15 and then sine of 40 and then j hat. So when you plug in the numbers, your F, the force magnitude for this external force is 11.49 I hat, and then minus 9.64 j hat. Okay, so if we look at this diagram, we can see that the whole block is moving rightward. It's not moving in the vertical direction, which means that the normal force, the gravitational force, and also the y component of this force, they should balance each other. So that's the equation. Let's say the net force in the y direction has to be equal to 0. So this equation basically tells you that the upward normal force plus the negative downward force of gravitational force, and then minus the plus the negative of 9.64, which is the Fy. The whole thing is equal to 0. So from there, we can actually calculate the magnitude of our normal force. So our normal force is this is 3.5 times 9.8, and then plus 9.64. So your normal force should have the magnitude of 43.94 Newton. So once you have the normal force, then plug into this equation. So you have 0.25 and then times 43.94. You should have your Fk. So your Fk has a magnitude of 10.985 Newton. So you have your horizontal force that's acting in the leftward direction, and you have the positive rightward direction coming from the external force. So the difference, the net force in the horizontal direction will give you, so using the Newton's second law, the net force in the x direction will give rise to acceleration. So this is your net force, so that's fine. What are the net forces? The net forces in the horizontal direction, you have your Fx, and then plus negative Fk, because Fk is in the opposite direction. So your Fx minus Fk, that will give you Mi. So Fx is 11.49. Your Fk we calculate to be 10.985, and that's equal to the mass 3.5 times A. So your acceleration is 0.144 meter per second. Okay, so that's the part B. Part A, the frictional force is 10.985 Newton. Okay, so this is again a very standard, equations. First of all, sum up all the forces in the x direction and the y direction. If it's moving at a if the net force is not zero, which means that it's going to give rise to an acceleration. In this case, in the vertical, there's no acceleration. In the horizontal, there's a non-zero acceleration. So you need to, in the vertical, since there's no acceleration, the net force sum up to be zero. And in the horizontal, the net force give rise to acceleration. So just find out what are the force terms in this net force to give to give the acceleration. Okay. So that's problem 9. And the next one we want to do is problem 11. Okay. And so let me just erase this. All right, problem 11. A 68 crate is dragged across the floor by pulling on the rope attached to the crate and inclined 15 degrees above the horizontal. So the diagram again is you have a crate on the floor and the force now is in this direction. Okay, and the mass of the crate is 68 kilogram. And the angle here is 15 degrees. All right, so if the coefficient of static friction is 0.5, so mu s is 0.5, what minimum force magnitude is required from the rope to stop the crate moving, and if mu k is 0.35, what is the magnitude of the initial acceleration of the crate? So part A, for part A, the whole thing is stationary and is at rest until you apply enough force to, that overcome the maximum static friction, so that the crate will move. And then part B asks, once it's, when it starts moving, what will be the acceleration, when it starts to move. So again, we need to draw a free body diagram based on the information we're given. Okay, so I'm going to take the star as the center of the block. It has experienced gravitational force, and there's external force, and there's a normal force, and that's because the whole thing is, the attempted motion is rightward. If it is attempted motion is rightward, which means that the friction force has to be in the opposite direction. So you have the friction force that is leftward. In this case, we want to find what will be the maximum static friction. Now, once the force is greater than the maximum static friction, then the whole thing will start to move. So you're asked to find what is the minimum force that will get this whole thing moving. Okay. So you can see that this is actually very similar to what we had, for problem 9, except that now the force is in that direction. And the force magnitude is not given, so you just have to assume that it has a magnitude F, and then you have the x component, you have the y component, and the x component and y component, will give you what they are pointing in a direction that has the 15 degrees, making it 15 degrees to the horizontal. All right, so part A, when the whole thing is not moving, which means that the net force in the horizontal direction has to be 0, and the net force in the y direction has to be 0. Now that's resolve this vector. So this force has two components. This is your Fx, and then this is your Fy. So Fy pointing upward, so we can see that that's applied to this. You have the normal force, which is upward, and then plus the Fy, the y component of that force, and then minus mg, the whole thing will balance each other. So this is how you find out your normal force. So your normal force, so we'll leave it like that. Okay, so you have that. Now, what about in the horizontal component? In the horizontal component, we can see that you have the Fx, you have the maximum static friction. So these two should balance each other. So you have your, so for this, you should have your Fx minus the maximum static friction. That will give you 0. So what is the maximum static friction? The maximum static friction is simply equal to mu s times your m value. Okay? And so in that case, do we have enough information that we can do? So let's see. So your Fx is equal to mu s and then times the normal force. So what is your normal? So times the normal force. And this one you have your Fy. That's equal to mg minus the normal force. Okay. So so in that case we can have let's see, what do we have here? So what we can do is that replace our end. We can actually replace our end. So you know what? So maybe the best thing to do is that, let's say n is equal to mg and then minus Fy, and then we're going to replace n with that expression. Okay, so your Fx is equal to mu s, which is a given number, and then times your mg minus Fy. Okay, so what do we get here? So then your Fx, what is your Fx? Your Fx, so your F here is equal to Fx I hat vector F and then plus Fy j hat. So we're going to express our x and y component in terms of the main to F, because this will have a common factor, that is the force main to F. So you have the x component is your F times cosine 15 degrees, because it's adjacent to the angle I hat. And your y component will have F times sine of 15 degrees j hat. So in that case, this, we can rearrange that. So Fx is this. You have your F cosine 15 degrees. Cosine times 15 degrees, that's equal to mu s 0.5, and then times mg 68 times 9.8, and then minus your Fy. Fy is F sine 15. So you can see that you have the common factor F here and that. So you can actually rearrange this. You have your F, and then you have your cosine 15 degrees, and then plus 0.5 times sine 15 degrees. And the whole thing is equal to 0.5 times 68 times 9.8. So after you punch in the calculator, you should have your force main to, that's equal to 304 Newton. Okay? So you can see that setting up these two equations is easy because it's based on the Newton's second law. And then how you go from there, you need additional information, which is this. When you express force in terms of the main to force, and then you have the angle is already given, so you can just use express the x component in this and the y component in that, and then substitute to this equation, so that you have just one unknown, and then you can just find out your force main to, which is 304 Newton. So when the force main to is 304 Newton, it's just enough to overcome the maximum static friction, so the whole thing is going to move. When the whole thing starts to move, we know that this is no longer true. The net force is equal to 0, no longer true, because now you have a non-zero net force in the horizontal direction. So in that case, what is the acceleration? So let's look at this again. So to draw the free body diagram for part B, you will have this force. You have now it's still moving rightward, so it's subject to frictional force, but that frictional force becomes a kinetic friction. So you have your Fk, and then you still have your mg, and you still have your normal force. So in that case, how do we find the acceleration? The acceleration is just basically the net force in the horizontal direction. That's equal to ma. So you have net force here. That will be your F times cosine 15 degrees, and then minus Fk, and the whole thing is equal to Ma. Okay, so how do we find Fk? Your Fk is equal to mu K. Fk is mu K times the normal force. So what is the normal force? The normal force, of course, of mu K is 0.35. And your normal force is equal to, so go back to this equation. This equation doesn't change. Okay, so you have the normal force that's equal to mg minus the y component of the force. So this is equal to mg minus fy. Okay, so now what would that be? So after you plug in the 68 times 9.8 and minus 304 times the times sine of 15. So your normal force after you plug in the number is, so let me just write it down. So when you plug in the numbers, your normal force will have a magnitude of 587.7 Newton. Okay, so this is a numerical value of the normal force. So once you have the normal force, and then multiply by 0.35, you should have value, which I did not calculate. And then once you have that, you can plug into this equation. So you can calculate your this. So let me just write it down that your A value, your A is equal to the F cosine. So F is 304 cosine 15 degrees. And then minus Fk. Your Fk is, is 0.35 times the normal force. The normal force is 587.7, and then over the mass. The mass is 68. So after you do that, your acceleration becomes 1.29 meter per second squared. Okay, so this is in a lot of ways, very similar to the previous problem, except that now the force is not given, so you have to assume that you have the x component and the y component, and then go from there. Okay. So the important thing is that draw a free body diagram and set up your equation according to the free body diagram. Okay. All right. Now, the next problem we're going to do is problem 16. So let me just. All right, problem 16. A loaded penguin sled weighing 80 Newton rests on the plane incline at an angle that's 20 degrees to the horizontal. Between the sled and the plane, the coefficient of static friction is 0.25 and the coefficient of kinetic friction is 0.15. So let me draw the diagram. So you have this, and you have this, the penguins, and this angle theta is 20 degrees. And you have the mu k, the mu s is 0.25, and the mu k is 0.15. All right, so you're asked to find, okay, the weight of the sled with the penguin is 80 Newton. Okay, so what is you're asked to find the least magnitude of the force parallel to the plane that will prevent the sled from slipping down the plane. So part A is that to prevent it from, what will be the force along this direction? This is external force. What is the force along that direction that will prevent it from sliding down? So the attempted motion is going down. If the attempted motion is going down, which means that the frictional force has to go upwards. Okay, so because it hasn't been moving, so it's just the friction that you experience is what we call the static friction, and you'll also find the minimum force. So again, that will be when the the frictional force is the maximum static friction. Okay, so let's draw a free body diagram again. Before we do that, let's draw the x and y. Again, whenever you do an inclined plane, you want to define your x and y axis so that your x-axis is along the plane and your y-axis is perpendicular to a plane. So let's do that. So this is your x and y. This is your x, and this is your y. So you have the force that's along the plane, and we just mentioned that because it's prevented from sliding down, which means that the friction force has to go up. So we have the static friction, which between the block and the incline. So I'm going to move that to here. So you have your F, and then that's the maximum static friction. Okay, and you have gravity. So that's your weight, and then you have your normal force. So again, altogether, you would expect four forces acting on this object, and so you're asked to find what would be the applied force B, so that the whole thing is not moving. Okay, so how do we set the equation? So you have the normal force here, you have the weight, this is angle theta, so which means that this angle is theta. So the weight will have two components along the new x-axis. So you have the downward x component, you also have the downward y component. Okay, so in the horizontal, the net force in the horizontal has to be 0. In the vertical, it also has to be 0. So from this equation, we have the external force, we also have the maximum static friction force that's pointing upward, and then that should be balanced by the downward gravity component along the horizontal plane. So you have your F plus the maximum static friction, and then minus or plus negative of W, and then this is the opposite the angle, so that has to be sine theta, and the whole thing is equal to 0. Okay, so we have that, and your task is to find what your F is. So W is given. We don't know the maximum static friction yet, so we need to. So what is the maximum static friction? So maximum static friction is equal to mu s times n. So you need the information of the normal force. To get the information normal force, we know that in the vertical, the normal force is balanced by the y component of this gravity. So you have your normal force. So normal force, and then minus your W, and this component is adjacent to the angle, so you use cosine. So you have cosine of theta, and the whole thing is equal to 0. Okay, so once you've done that, we know that the angle is given and the weight is given. So what is your normal force then? Your normal force is equal to W times cosine theta. So you'll have the 80 times cosine of 20. So your normal force, you should get a value that is equal to 75.18 Newton. And once you have that, then you can plug into this equation. So you have 0.25, and then times the magnitude of normal force, 75.18. So you should have the maximum static friction that has a magnitude of 18.79 Newton. Now, once you have that, then you basically you can solve for your force, because this one is equal to F is equal to W sine theta, and then minus the maximum static friction. So you have W, which is 80, and then sine of 20, then minus the maximum static friction, which is 18.79, and then so your final answer. So your F here, you will have 8.56, 567 Newton. So that's the force magnitude. That will be the force to apply to this this system, so that the whole thing is not sliding down. Okay. Okay. All right. So that is that. So that's your part A. Now, for part B, let's see what the part B is asking. For part B, what is the minimum magnitude force that will start the sled moving up the plane? So if the whole thing is moving up, which means that now the force and the whole thing is actually moving when it's, to start, let's see, it's not moving. So it will start the sled moving up the plane. So again, you will have to find the maximum static friction. Now, if the whole thing is moving up, which means that your frictional force now has to be in the opposite direction. So now your maximum static friction, because the static friction is always in the direction of the attempted motion, and the attempted motion now is moving up. It is moving up, which means that you have the maximum static friction that's pointing in that direction. So that will be this. So you can see that you still use your use this set equation. The only difference is that instead of adding the maximum static friction to the external force, now it's actually pointing in the opposite direction. So the only thing you would change is this. So I'm just going to continue to use that. So you still have that, but now the force and the maximum static friction, they are now in the opposite direction. So minus that. And then the gravitational force now is along the same direction as the maximum static friction. So now once you have this, so this, you add them together. So you will have a value. And the maximum static friction is there. And then you can see that in the y component, it doesn't matter because the y component in the vertical direction has nothing to do with the horizontal component. So you still have this. Your normal force does not change. Therefore, your maximum static friction, the magnitude does not change. And then the only thing that changes is the signs in front of the maximum static friction because now it's moving, up. If the whole thing is attempted to move up, which means that the static friction is trying to, pointing in the opposite direction. So now you have this. So then becomes quite straightforward. You just have the, plug in the numbers. So you should get a magnitude that's 46.15 Newton, okay, as opposed to the whatever number that we had previously, okay? So, W here is 80, so I'm not going to plug in those numbers, and then this is that. So the other thing is that instead of minus here, you use a plus, so you got that, okay? So that's your part B, okay? Now, part C says what value of F is required to move the sled up the plane at constant velocity. Now, the whole thing now is moving up, but at a constant velocity. So part C here is that now it's moving at constant speed. When it's moving at constant speed, what it means is that acceleration horizontally has to be 0. If it is moving, moving out constant, at constant speed, then you have this. And also in the vertical, it's not moving in this direction. So in the vertical direction, you still have that. So your M minus, so this force, normal force is balanced by, the gravitational force in the vertical direction still holds true. So your normal force still has this magnitude. Now in the horizontal direction, the net force has to be equal to 0. And it's moving. If it's moving, then it is not the maximum static friction that you want that you work with. It's actually the kinetic friction. So the kinetic friction is equal to mu k times normal force. Your mu k is 0.15, and your normal force you calculate to be 75.18. So when you calculate this, your mu k should have the value. Let me see, do I have the value? I do not have the mu k value, but something, okay? And then let's look at the free body diagram. If it's moving up, which means that the whole thing experiences kinetic friction and it's opposed to motion. So your kinetic friction, so this is your kinetic friction. So in other words, your equation now becomes the upward external force, and then minus your Fk instead of maximum static friction because it's moving. Now it's minus Fk, and then minus W sine theta because this force is downward in the downward direction. So F minus Fk minus W sine theta. So what you have here, so I'm going to move it down here. So you have your F. What is your asked to find? You also find the force. So F is equal to your Fk and then plus W sine theta. Okay, so Fk is just this, mu k times the normal force, and then plus the W sine of 20 degrees. So after you plug in the numbers, so I can just rewrite it here, 75.18, and then plus 80, and then sine of 20 degrees. So the force that you apply, so the whole thing is moving at a constant speed, is equal to 38.6 Newton. Okay, so that's a force. That's a force that would be just to have the whole thing moving upward and at a constant speed. Okay, so that is that.